Let me welcome everybody on behalf of the Department of Geology, Geography, and Environmental Studies at Calvin University to one of our Friday afternoon seminars. And for today, we're very excited to have with us Adam Koster, who we first got to know back a few years when he was a geology major in our department. And he graduated with a Bachelor of Science in Geology in 2011, and then went on to Idaho State University to do a Master's of Science in Geology. He's had a few interesting positions since that time, and he's currently working with the United States Air Force at the National Air and Space Intelligence Center. And I think I will just stop there in identifying what he's doing because I certainly don't have the security clearance levels that Adam does. He's not necessarily going to be talking about his particular work there, but he is going to be talking to us about imagery science more than just pixels. So Adam, assume that there's loud rounds of applause coming from every screen that is looking at you. And we're looking forward to hearing what you have to say.
All right. Well, thank you, Professor Van Dyke. As it says, I'm going to be talking about imagery science. And so I'm going to actually start out by just giving you a little bit of background of myself and of imagery science in general. And then I'm going to go through some of how it works and some of the fundamental underpinnings of it, talk through the lens of the spectral features of minerals. And then I'm going to get into a little bit more application, how we use those spectral features of minerals to actually do practical things. And then finally, I'll get into some conversation about ground truth and field work, because I may not deal with rocks every day, but I still believe that field work is important, and I absolutely love field work. So every time I get to do it, I get really excited about that. So as Professor Van Dyke said, I attended Calvin College, Calvin University now, and born and raised in Grand Rapids, Michigan, moved out to Idaho, got my master's at Idaho State University. And then in July 2014, I moved to Dayton, Ohio to work for the US Air Force. Worked for a couple of defense contractors for a little bit, and then I became an Air Force civilian in 2016. I've been doing that ever since. So that's kind of a little bit of a taster of my career. Personally, in moving down to Dayton, I actually met my wife at church in 2015, and we were married in 2017. And on Wednesday, we'll be celebrating the first birthday of our son Logan. So that's my family right there. We went pumpkin picking for Halloween. So moving on to image science. So what is imagery science? So when I work, we have two types of analysis we do on imagery. There's literal analysis and there's non-literal analysis. So literal analysis is looking at your image and saying, that's a car, that's a tree, that's a rock formation, or a rock unit or something like that, rock feature. Whereas non-literal helps you tell what that rock is made of, what that car is painted with, if that tree is healthy or not. So an example of this is that set of images on the right. So that's from Menelaus et al. 2014. And the top image is a thermal image captured with a ground sensor. And you can see some clouds, you can see the mountains, you can see maybe some vegetation and a road in there. But through special processing, we're able to go beyond that literal interpretation to actually say, oh, wow, there's some gas plumes in that image. They actually released some gas for some testing purposes. And you can actually see through some image processing, okay, this is where that gas is going. This is perhaps even the composition of that gas. So what we do here is we look at more than just what's in the image. We look at those pixels and we say, okay, what can the information contained in those pixels tell us? So most imagery comes down an image cube like you see at the left. That's a lot of information that you need an image science person, an imagery scientist, to actually look at and interpret. And it's really quite amazing some of the stuff we can tell if we're given sufficient data. So the background of imagery science is the electromagnetic spectrum. So as you know, light has the wave particle duality of light. It's both a wave and a particle. For our purposes, we'll be mostly concerned with the wavelength. So this the wave phenomenology. So as you probably are aware, if you're taking the remote sensing course, you have shorter wavelengths, higher frequency, light, those gamma rays, those X-rays, those are higher energy. And then as you start increasing your wavelength, lowering your energy, and decreasing your frequency, you get into X-rays, ultraviolet, and the visible. So what our eyes can see. As you move beyond to even longer wavelengths, you get into the infrared, the microwave, and the radio waves. So the region we'll be looking at mostly is in the visible to near infrared and shortwave infrared. So this is what's called the reflected portion of the spectrum. So what do I mean by that? So light comes in from the sun. It interacts with the atmosphere. And as you can see in that upper right image, you get light, it goes through the atmosphere. In the lower right image, you actually see this plot of, it kind of looks like these hills and valleys in there. So those valleys where it's light, that light blue, those are zones where the atmosphere is totally absorbing of light. So that in the regions we're interested in is caused mostly by water, though carbon dioxide and ozone do play a part. As you get towards longer wavelengths, such as the mid-wave infrared and the long-wave infrared, you get different atmospheric gases and particles actually playing a role in that absorption. But for now, we'll focus on the reflected portion. So that light goes through, it gets scattered, absorbed by the atmosphere, and it interacts with the material on the ground. So three things can happen when that light interacts with the material on the ground. It's either going to be absorbed, it's going to be transmitted through the material, or it's going to be reflected. Now, there's a fourth thing that happens, and that's called emission. So objects on the ground can emit light. This is the basis for your, say, your thermal cameras. That I think the engineering department at one point had one. And basically, if you pointed at, like, say, a person, you'll see they're glowing red hot. Hopefully not too hot, but that's light being emitted in the mid-wave or the long wave region that is getting picked up by that sensor. That's not being reflected off them, it's being emitted by them. So once that light gets reflected, it goes back through the atmosphere and it encounters our sensor. So that sensor can be somewhere on the ground, it can be in an aircraft, it can be in space. And to correct or to process this data, we actually, to make it so it's useful for us, we actually have to remove the atmosphere. And there are several ways we can do that. So I think Professor Van Horn, correct me if I'm wrong, is still using AirDOS. I'm familiar with both AirDOS and ENVI. Both, I believe, have capabilities to remove that, or at least mitigate the effects of the atmosphere. So once we have that in reflectance, then we can actually start that data in reflectance. We can actually start telling you what characterizing the material that we're looking at. The nice thing is with materials is dependent on their chemistry and their structure and a number of other things, they will absorb and reflect light at different wavelengths. So we can actually use that to identify and characterize them. So one of the crucial parts, of course, of remote sensing is the sensor itself. So I'm primarily going to focus on spaceborne systems, though there are airborne systems, and I'll actually mention one of those in particular. And one of the things we talk about when we're talking about imaging systems is resolution. There are 4 types of resolution. And the first type is spatial. So this is the one you probably often hear about. Spatial resolution literally means just how big of an object can you see? Can you see a bus? Can you see a car? Can you see a bicycle? Can you see an oil tanker? Stuff like that. And in today's world, you have your standard Landsat type imagery, USGS and NASA standard civil sensor, their highest resolution is about 15 meters. You go towards more commercial systems like Worldview 3, that's by Maxar. Their best resolution is about 0.3 meters, so 30 centimeters or so. So you can see a lot. You can see a lot with that, and that's really quite good resolution. The next part, or the next resolution thing that's really important for image science is spectral resolution. So each of these sensors, they collect imagery in discrete areas of the electromagnetic spectrum, and it collects them in bands. So they measure energy in these little areas, and we'll call those bands. They're anywhere from 10 to up to 100 or 100 or more micrometers in width. And think of those as just measurements being taken. And there's for our purposes, there's two broad types of spectral resolution. The first is multispectral. So most of your civil sensors, your digital globe constellation, your Landsat, your Sentinel down there on the left, those will collect multispectral. So Worldview 3, for instance, has 16 bands, a multispectral group that collects in the visible to near infrared. So for our purposes, about 400 nanometers or 0.4 micrometers of wavelength to about 1,000. And then the shortwave infrared, which is we'll say about 1,000 or so to about 2,500 nanometers or 2.5 micrometers. There's Landsat and Sentinel and Aster have similar, are a number of other sensors that have similar collection capabilities, similar band placement. Landsat also has a thermal infrared band that has a 100-meter spatial resolution. So the other version of this is hyperspectral. So hyperspectral collects, instead of tens of measurements, hyperspectral collects hundreds of measurements. And we'll actually see this later as we go through the briefing. We'll actually see hyperspectral first, and then we'll see multispectral, and I'll actually go back a bit to hyperspectral. But hyperspectral gives us the ability to actually discern very small features because there's so many of those measurements. So let's think of it as you have points that you're collecting, and then you have to draw a curve through those points. So the more points you have, the smoother your curve is going to be. The more points you have, the more of those absorption features you can find, and through that you can actually do some what might be called fingerprinting or pattern matching, which will actually help you identify a material. Multispectral, you can do that in some cases, and we'll cover that in a minute. But there's other things you can do that in multispectral that are more useful for characterizing. Some examples of hyperspectral sensors would be Earth Observing 1 Hyperion. That's a hyperspectral sensor with wavelengths with coverage in the visible to shortwave infrared. NASA also operates what's called Avarice. It's an airborne sensor that they fly in their version of the U2 called the ER2. That's another similar sensor that it operates in the visible to near shortwave infrared. So the third one, and this is where you see a lot of really cool advancements coming, the third type of resolution is temporal. So that's how many times you can revisit a site, or how long it takes you to revisit the same site on the ground. So with Worldview 3, for instance, and that may be on the order of a week or so. It's probably a little bit less as advertised, but maybe on the order of a week or so. Whereas companies like Planet are operating a massive constellation of sensors. So down the right, you can see some of the sensors they have. So they have 130 or more than 130 of these little CubeSats called Doves, and they have some multispectral capability, so they can image in a few bands in the visible to near infrared. And I think they may have added some with their newer versions of them. They have 130 of those. They also have legacy rapid eye sensors, and they actually have a newer set of sensors called SkySat, which will have better spatial resolution and more spectral capability, I believe. But those sensors, they have the capability through all those sensors to actually image the surface of the Earth once every day. So that's huge in terms of repeatability, in terms of the amount of data you can get in. There's certain companies, for instance, that will do what's called car counting. They'll use data like this, where they'll take pictures of, say, a Walmart parking lot, and they'll count cars. They have algorithms that do it, and they can use that to say, okay, today this many people patronize your establishment. The next day, the next day, the next day, and so on. You can actually use that to drive just how well your establishment is doing if there's a lot of cars in your parking lot quite frequently, for instance. The point of this is, with all this data coming to us, and it's high quality data, we need a lot more methodology than just opening up a single image in whatever processing software you choose to use. We need things like AI, artificial intelligence and machine learning to actually help us analyze these. And one of the jobs of imagery scientists is to develop the methods and the algorithms to actually help process this data. And then there's that fourth type of resolution, that's radiometric. That's just how sensitive your sensor is. How the sensitivity of how much light, it corresponds to gray levels in bits. So 16-bit, 11-bit, etc. So that covers kind of the sensor aspect of it, the sensor and the background aspect. Now we're actually going to get into kind of the basis of what we're doing here. So I'm going to start talking about the spectral features of minerals. So first thing, I'm using minerals as an example because I'm a geologist, so I like to talk about rocks and minerals. The spectral features of minerals are easier to constrain, and since rocks are made up of minerals, the spectral features of rocks will broadly reflect the mineral composition of that rock and whatever weathering is occurring to it. So apart from that, I mean, we should care about the spectral features of rocks and minerals because there are implications for remote sensing, and their use in mineral mapping, for mining, for oil and gas as exploration. They also have implications for natural resource development, and even some environmental aspect, or very much actually environmental aspects. For instance, acid mine drainage. That there are certain minerals which are products of that, which you can actually detect using certain remote sensing tools. That being said, the features I'm going to talk to you about, while they may occur in minerals, are not necessarily constrained, and they're not necessarily the only spectral features or the only causes. But what I hope you get from this is we can use the absorption features of a mineral or a plastic or a paint to tell you what's in that paint if we have enough spectral resolution. And towards the end of this part, I hope that you'll actually be able to see that just because we can't fingerprint a material doesn't mean we actually can't map it or can't tell it apart from other materials. So without further ado, let's get into some of the spectral features of minerals. So there's two broad processes here we're going to work with. The first being electronic processes. Electronic processes have to do with energy coming in. So energy at a given wavelength energizes an electron differently. So as you know, minerals, they have that crystal structure, that crystal lattice, and there's ions and such in there. And you know, those electrons and those ions and atoms will get energized and cause spectral features. So there's four electronic effects. The first is crystal field effects. So these are caused by electrons in the outer shell of an ion. So in the outer shell, they're kind of out there on the very edge. They're not shielded by the other electrons that are closer, like those that are closer to the nucleus. So what happens to these electrons is they are actually subject to and influenced by the other ions in that crystal lattice. So these are called crystal field effects. So that interaction between the crystal lattice and the electrons in a given atom are going to be cause spectral features. An example of that will be those of olivine. So you can see that green signature there. The area of the spectral feature, which is actually several, is highlighted in red. Now, the crystal field effects are most common in minerals that contain metals, such as iron, nickel, cobalt, chromium. The other thing I actually want you to see, and I should have started this, is these are hyperspectral signatures. These are derived from the USGS spectral library. So there's literally thousands of measurements in there. So very smooth curve. Moving on to the second type of electronic process, and that type is charge transfer. So what happens here is an excited electron, one that has taken in energy, moves throughout the crystal lattice, and that causes spectral features. Usually these occur in the UV or near the edge of what we will, of the visible, and they manifest themselves, these features manifest themselves as usually a drop off towards the ultraviolet, towards the higher energy portions of the electromagnetic spectrum. So you can see there in the spectrum of limonite, you can see that dip towards the UV at about, starting at about 0.5 micrometers and going towards shorter wavelengths. Color centers. So this is the next type. Color centers are very interesting. They're also can cause some heartburn among mineralogy students. So when in grad school, I heard a story of a certain enterprising mineralogy professor who decided that they wanted to instill in their students that color is not necessarily the best diagnostic tool when trying to identify a mineral. You're much better with cleavage, hardness, and streak, for instance. So instilling them this, they put on several different colors of fluorite. Fluorite is, in my opinion, rather infamous for having numerous colors. So for the mineralogy students out there, I apologize if I gave Professor Sparks an idea, or Professor Sparks, I apologize if I ruined something, if I had a spoiler in there. So the reason this is because of crystal lattice defects. So color centers are caused by crystal lattice defects. They're not really caused by the chemistry or the structure, but the crystal lattice itself. So depending on what the nature of the defect, and as you can see, it causes a little dip. And you can see that in the spectrum of fluorite, that purple signature there. And the nature of that defect will actually cause that absorption dip to actually move to longer or shorter wavelengths, giving fluorite its multitude of colors. And the final one is actually, to me, particularly interesting, and that is the process called conduction band transition. So in some crystal lattices, you actually get a smearing out of energy amongst the higher energy shells and energy electron shells, and that energy usually splits into two different levels. So there's bands. So there's a conduction band of really high energy electrons, and there's a lower energy valence band. So the conduction band, those electrons are free to move about the crystal lattice, as opposed to the valence band, where those electrons are very tightly bound. So what this means for us is, depending on the energy state, you can actually have a feature. And that feature is caused by a little gap in between those two bands, called the forbidden zone by some. Basically, it's a zone where electrons cannot assume that energy. And you'll see this, for instance, so in metals, there really isn't that gap. Because those electrons are so high energy, then they're moving around the lattice of the metal, they're not actually going to have a gap there, so they're all going to be conduction. However, on the opposite end of that, you have dielectrics, which the valence, or those electrons, our valence electrons, are very tightly bound, so the amount of energy you need to actually get them into a conduction band is going to be really high, and that feature caused by that forbidden zone, that transition between conduction and valence, is going to be very broad. And typically, that feature will only occur in the, or for dielectrics at least, in the UV or shorter wavelengths, those higher energy wavelengths. However, there are intermediates. So semiconductors, for instance, like sulfur here, though that gap will actually show up in areas we can observe with, say, world view 3 for in the visible to shortwave infrared. And you can see it there is actually a really classic feature of sulfur, a very sharp increase towards the yellow, gives it that yellow color. And that feature will be sharp, or it will be kind of muted depending on the purity of the sample. Other minerals, I think stilbite has a feature like this as well, and that one's all the way across into the shortwave infrared, or near enough. So that's kind of a really interesting one, because through it, if you have enough spectral coverage and spectral resolution, you can tell if a mineral, potentially tell that a mineral is, okay, this is going to be a good conductor, this is going to be a good dielectric, or this is an intermediate form. So just one of the little kind of cool things you can do with if you know just what is causing the spectral features in a given sample. So that'll wrap up electronic processes. The next one we'll do is vibrational processes. Now, vibrational processes occur because the crystal asses randomly vibrate, but they only have a few select motions in which they can vibrate. And when energy comes in at a given wavelength, those crystal asses get excited. They get more energy, those bonds get excited, and they vibrate faster. And that vibration causes what are called overtones. Those overtones will occur in various portions of the electromagnetic spectrum. Sadly, for our purposes, major rock forming elements and their oxides, such as silica, aluminum, and magnesium, those overtones will only occur in the longer wavelengths of the long wave and the mid wave. So we won't see features of them. So you won't see a feature of, say, feldspar or quartz in the visible to shortwave infrared, unless it's got included water in it. So bringing that up, water is, however, one of those things that actually does create overtones in the visible to shortwave infrared, even into the near infrared, actually. So water has a number of fundamental modes, and when it vibrates, you can see the spectral features it produces in the regions we're interested in. So there's several in there. Several of them are very large. Sadly for us, if you remember back to our atmospheric window diagram where the atmosphere absorbs, or where the atmosphere doesn't absorb, several of those features, notably at 0.9, about 1.3 to 1.4, and about 1.9 micrometers, several of those features, that's areas where atmospheric water will absorb light coming in from the sun. So you're not going to see those features in the wild. Only really under lab conditions or in an area where you have very little atmosphere. That said, there's still several other features in the sphere which we can use, and actually we will use them to separate different minerals from each other. Another one is hydroxyl. So hydroxyl groups, depending on what they're bound to, the geometry of the crystal site they're in, and the energies of the electrons in crystal lattice, will also cause spectral features in the shortwave infrared. Now, hydroxyl only has one fundamental mode. However, it does create a distinct feature, and for this case, I actually chose gibbsite and brucite to illustrate the fact that depending on what the hydroxyl is bound to and the crystal site it's in, you can actually move that hydroxyl feature to different locations. So gibbsite, the aluminum hydroxide, has a gibbsite, the aluminum hydroxide has a feature at about 2.3 or 2.2, 2.23 or 5, whereas brucite has one at 2.3. So, and we'll actually use that very much in the coming slides. The final vibrational process though I wanted to talk about was carbonate. So carbonate has classic features for among spectral scientists, at least, at about 2.3 and 2.5 micrometers. And we use these extensively to determine what kind of rock or mineral we're looking at. So with that in mind, let's take a look at some practical ways we can use this information. So what I did is, when I was preparing for this talk, I basically just rated the USGS spectral library, and the Jet Propulsion Lab has one as well. I rated that and basically just took all the signatures of minerals that they had, or rocks that they had, and I used them for some examples here. So the first one is I created some band ratios. So first off, what I actually did to make it simpler for myself is spectrally resample that hyperspectral data that you saw earlier to the spectral resolution of worldview 3. So instead of 1,000 bands, I'm now only playing with 16. So in some ways I handicapped myself, but it actually made it a little bit easier with the data reduction. So worldview 3, sadly for our carbonate detection, does not have that 2.5 micrometer band. It does have one at 2.3, but that should be sufficient for what we'll use it for. So you'll see in these, in the labels for the X and Y axis, you'll see something like S6. That refers to worldview 3's 6th shortwave infrared band. So one of the things I love to do is play with band ratios. In the simplest form, a band ratio is taking the response or the reflectance in one band, say blue, and dividing it by the reflectance or response in another, say green. The ones I actually have here are a bit more complex. They're called normalized difference ratios. And I do that usually just to if I'm trying to compare image to image to image and data from multiple scenes and multiple days under multiple conditions, that form of a band ratio actually has an ability to actually kind of standardize or to normalize certain things. So it's very useful in that regard. It's a bit better than doing, say, S6, just S6 minus S8, SWIR 6 minus SWIR 8. So what I did here is I chose 4 bands to play around with, the first being SWIR 6 and SWIR 8, so along the x-axis. Now, because there's that absorption feature for carbonates in SWIR 8, and there isn't one in SWIR 6, carbonate should have very high value or higher relative values in this band ratio. And you can see the blue dot, or the blue points in there. Those do tend to have higher values. Now, there is some mixing down towards about 0.5, and that's to be expected because nature isn't as clean as we'd like it to be. But in general purposes, it works. The other thing I did was S5 and S7. So those are designed to capture a feature in that 2.2 range, kind of a hydroxyl feature, which is most likely caused by weathering. So for the felsic intrusive, granite, you'll weather, feldspars will weather to clays, and those have hydroxyl, and members also have some water depending on the clay. Sandstones, if you have feldspar in them, and other silicic rocks will have those if they contain feldspars or other minerals that weather to hydroxyls, minerals with hydroxyls in them. So for the most part, you're seeing are non-carbonate. It's in the red and the green. Those right here are plotting much different than the vast majority of, or than the majority of our carbonates. There's a couple up here. These probably have sandstones up here. Those probably have carbonate cement or something like that are causing them to plot up there. So using this method, you can actually say, create a map of carbonate versus non-carbonate. And I'm not sure how it works in AirDOS, but in Envy, you can create a band ratio like this. It will input that. It will output a black and white image where your black pixels, your darker pixels are going to have lower values. Your lighter pixels, your white pixels are going to have higher values, and and you can mess around with some settings in there to actually get it to pop out different values, and use that to actually get an idea of what you're looking at. And I'll actually give you an example of that someone published a little while ago. So let's look at some more of these real quick. So Hydroxide minerals, so we've seen the signatures of those in hyperspectral. So again, gibbsite and brucite. And you can also see them now in World V3. So again, not as smooth of a curve, but they should be able to actually get us to where we need to be. And what I'm keying in on here are those features in those 4 bands in the longer side of the shortwave infrared, and basically keying in on some of those those features in there. And I did this basically, one, because I knew how the minerals reflected and absorbed, but also because I was able to actually kind of look at it and do a little trial and error real quick, and actually develop a band ratio where it's pulling those 2 apart. So in these band ratios here, as you see on the X and the Y axes, those band ratios will cause Gibbs or brucite to plot negatively, and gibbsite, or at least on the x-axis, and gibbsite to plot positively. So in an image that you would output for this, gibbsite would probably have lighter value, or brighter, would be brighter, whereas brucite would be darker. A little bit more. That was kind of a simple one. Here's a bit more complex. So kaolite versus smectite clay. So I have one kaolite, I have kaolite, and then 3 smectites. And so the kaolite ratio, this ratio I developed, or I did again a little bit by trial and error, but you're actually getting it to the kaolite to plot above 0 on the y-axis. Kaolite, of course, is being anhydrous, whereas the smectites have water attached to them. So that it's probably keying on those features. Montmorillonite is plotting differently than the other 2 smectites. I speculate here, and that's possibly because different elements are bonding to the hydroxyl in that mineral. And this would be something you'd be interested in looking for, say, if you're looking at Mars, for instance, trying to figure out what kind of clays there are there or what kind of clays are there as evidence of, hey, are these clays hydrated? Okay, well, or have water attached to them? Oh, hey, if they have water attached to them, that means at some point there was flowing water on Mars. And people have actually done work similar to this. And finally, we'll get to another sheet silicate, micas. So I plotted 4 different micas: biotite, glauconite, muscovite, and lepidolite. As you can see here on the x-axis, biotite is much different than glauconite, which is slightly different than lepidolite, muscovite. And again, that's probably due to what the hydroxyl is bound to in those different micas. Interesting thing with the lepidolite, as it contains lithium, that might actually be something that people who are economic geologists might find interesting as something we could mine, perhaps. Also note that I actually used near-infrared bands for this, so I didn't just stick to the SWIR. So I talked a lot about, I showed you some plots. So those are all they're all well and good if you know what you're looking at, and if you have distinct targets that you want to plot against each other. But what if I just wanted to map something? Well, back in the 3000s, we had this the satellite called Clementine, which orbited the moon, and they were actually able to use the multispectral sensor on that to map different mineral content on the surface. So this is one of those diagrams mapping percent olivine. To do that, they used a ultraviolet band, which is something a lot of Earth remote sensing sensors don't have. And they used, I believe, 2 near infrared, or actually one would technically be a red edge. So it's right in that area between the red, what our eyes can see, and then the near infrared, what our eyes can't. And then there are these 2 near infrared bands. And they were able to ratio those, and they were actually able to get content of different oxides. And then they were able to infer from those just how mineral composition. And the cool thing about this one is, so on the left you have the lunar near side, and the right you have the lunar far side. So that olivine is showing up in distinct areas. Those actually correspond to the lunar mare. So those big basalt lava plains on the moon. And the areas where there isn't much olivine corresponds to the lunar highlands, which are primarily anorthosite. And again, being predominantly predominantly feldspar, those are not going to have obviously the same response as olivine. They do other ones with this, with actually where they map the feldspar and they map clinopyroxenes and orthopyroxenes as well, and you can actually see some distinct patterns, and you can infer different what's there on the surface. It's a very kind of useful example of how we would map minerals. So what if we don't want to map minerals? Well, here's an example here's an example where we didn't map minerals and instead we map something else. So September 11, 2001, terrorists crashed planes into the World Trade Center, the Pentagon, and also one went down in Pennsylvania. And shortly thereafter, NASA flew its Avarice sensor. So a hyperspectral sensor on their version of the U-2, they flew it over lower Manhattan to try to map just the debris from the collapse of the World Trade Center towers. So they didn't use band ratios for this. Instead, since the hyperspectral sensor enabled them to do some pattern matching. So as you can see on the right, we have these signatures of some materials. So you have cement, dust, gypsum board, gypsum board, and they can use those spectral signatures to basically go through the image. And there's algorithms which they used to go through the image pixel by pixel by pixel and map that reference signature to whatever that pixel signature was. Again, I'm not as familiar with Iridis as I should be, but I assume it would have some capability here. Envy, what I'm more familiar with, does have capability, and there are several different processing tools that have been developed outside of those two programs. Even ArcGIS has a imagery processing tool that can. I'm not sure if it can do this, but many other tools can. And as you can see here, until my mouse moves. So right here's a little plume of material coming out of the ground zero area. The difficult thing with this is you can see like cement and dust and concrete. Well, those are going to be found in any urban area. So mapping here is a bit more difficult. And these are things that are very similar to the materials that are actually there. So you can do this with, say, acid mine scenarios. You can do this with presumably volcanic dust, ash scenarios, forest fires. There's really a lot you can do with, if you have the right algorithm, the right spectral and spatial resolution, and a good working knowledge of the science behind the imagery, or the science behind that pixel. So one of the last things I'll touch on is ground truth. So as I said before, I love being outside. Tying me to a desk and forcing me to stare at imagery is all well and good, but at some point I have to be outside. You just can't kill that field work in a geologist, bug in a geologist. So one of the things I really enjoy doing is helping with ground truths. And ground truth works as a way to one, test how your sensor is doing, and two, develop new methods, new algorithms for instance, material detection, new band ratios, stuff like that. So I'll cover like the first side of it, calibration testing, telling how well your sensor is working. So every so often, Digital Globe, or I should say Maxar, who owns Worldview 3 and Worldview 2 and the rest of that constellation, and GeoEye, will do what's called vicarious calibration, where they have a cal site in Colorado, sort of near where their headquarters is in Denver, a bit more out in the rural area, away from the city. But they put down materials, and they basically image those materials with their sensor, and then they also use handheld spectrometers like the one you see at the upper left to take measurements of material, and then they of the material they put out, that tarp or whatever it was, and then they compare the two, and they can do some mathematical processing and among a number of other processing methods, and they'll actually update the calibration coefficients and the calibration factors for their sensor to account for any issues that the sensor may be having. So they've done several, or Maxar has done several calibration rounds since the sensor's been since the sensor was launched in, I think, 2014 for World V3. Another thing we do with it is we can put out, or you can put out, image scientists are the we. Image scientists, you'll put out materials you're interested in: paints, concrete, other building materials, metals that you might find in an aircraft or a car or a boat, plastics, all sorts of things. We set those out and we take measurements on them. So again, we use a spectrometer like that, and we can take a very good measurement. It's not necessarily lab quality, but it's very close to what you'd expect to see from a lab reflectance signature of that material. And then we can compare that to what our sensor collected. Either we fly a sensor, or you can fly a sensor over, you use a sensor on the ground, or you use a sensor in space. So one of the ways you can do this is, okay, let's have our ground truth, our data we collected from a ground spectrometer here that we know is pretty close, if not actually what the response of that material is in a given wavelength region. We can use that to kind of build up the theory behind it. So let's build a detector for the mineral muscovite. We take hundreds of measurements of muscovite, samples of muscovite we put out, and say you had a very large pile of muscovite for World V3. It had to be very large. But you take measurements of that, and then we develop algorithms, band ratios, stuff like that. And using those signatures, and then we can go over with our sensor, say it's World V3, and then we collect imagery, and then we apply those methods we developed using the library data, using the reference data to the sensor. So, okay, we can do this on the ground, can the sensor do it? So it's not only a capability assessment, but it's also hey, let's develop some new stuff. Let's develop some new methodologies. And that's one of the really fun things that image scientists get to do, is we actually get to not just look at data and tell you what's in it, but we actually get to figure out new ways of telling you what's in your data, whether that be material characterization or identification, or spatially telling what's what, using advanced algorithms to count cars or other materials, wherever objects we're interested in. We can do a lot of this, and a lot of it is enabled by advanced ground truth and field work. So hopefully, just wrapping up, hopefully through this, I actually was able to give you a good idea of what image science is. It's a very broad field and how it works. Hopefully you've also gained a little bit of understanding of what causes what you see when you look at a mineral, especially fluorite. And hopefully it told you that, or you see here that ground truth, that we do ground truth, and you don't have to sit behind a desk and look at imagery all the time. If you're an image scientist, you actually get to go outside, do field work. One of my colleagues who used to work at Maxar, he's since moved on to another company, was actually a geologist, and he and I bonded over that when I would go out to Denver to meet with him and his team. But he did his thesis on basically collecting samples with the spectrometer and then linking that back to imagery. So you can, if you're a geologist, you got that bug to go do field work, you gotta be outside. There's hope. You can do ground truth. You can do field work for imagery science, and you can get in the cutting edge of developing those algorithms and those methods for getting the most of your spectral data. So again, with that, I thank you for allowing me to talk with you today. It's great to see all of you, and I'll open up to any questions. So thank you.
Thank you very much, Adam. And I'm sure there's, again, a lot of clapping going on, and you could see some people sharing their screens or sharing their videos at this point in time. We have a little bit of time for questions. So if you have a question, you can either put it into the chat, or you can unmute yourself and ask that question. And Adam, it would be up to you if you want to keep on sharing your screen, or if you want to stop sharing it. You might be able to see a few videos of people as they're asking questions.
Yeah, yeah, I'll just run this one through. This is the references I used for the spectral features of rocks and minerals. There's actually a number of papers published in the 70s by like Graham Hunt and Jack Salisbury and others that were really great references for if you want to dig more into how different minerals look in the visible shortwave infrared. I have those papers if you'd be interested in them, just let me know. But I can stop sharing my screen, and there.
And I wonder if there's some remote sensing students out there who are coveting your bibliography right now. I'm sure they'll ask a question. I can ask a question, but it's going to be very basic level. Renee looks like she has a question. Go ahead.
Yeah, first of all, can you hear me?
Yes.
Okay, excellent. Adam, fantastic talk. Thank you so much for sharing that this afternoon and all the connections to mineralogy. Hopefully the mineralogy students really enjoyed and connected with that side of it. Having had a student that worked on lunar and spectral analysis there, and the geochemistry course also did a spectral analysis paper last spring. I wondered if you had any insight as to, you know, does it matter the sun angle? How is that accounted for? And that in dealing with spectral analyses, what place does that play in the processing?
Yeah, so I will say most of the time when I'm doing processing, I will assume that the material I'm looking at is reflecting equally in all directions. For the students out there, that's called Limburtian behavior. Now there are certain things you can do where you'll actually there are certain measurements you can take where you actually know the dependency on solar angle and sensor angle. But for the most part, I think a lot of people assume that that's uniform. World V3, I know, for instance, typically images pointing almost directly down or at nadir. Though I have seen the guy who I was talking about earlier at the end of the brief, he has a story he'd like to say where he took a very off nadir high angle shot where it was actually the side of this mountain in Japan, and he was showing it to some of his Japanese customers, and they all started freaking out because in Japan, apparently you pay for imagery by what the amount of material or by the amount of land that is in it. So they got a little bit worried at the cost, but yeah, for the most part, I assume very little solar angle. That said, it is something that you could work on. There's something that should be probably investigated and I think it's actually more important. It becomes more and more important in the longer wavelength regions as well. So I hope that answers the question. Thank you.
It does. Thank you. Appreciate it.
So, Adam.
Hey.
Hi, good to see you. How does surface roughness enter into your reflectance properties?
Yeah, that's so surface roughness will surface roughness does have an effect. It has more of an effect in I believe in longer wavelength regions such as the long wave infrared. That being said, if you there is a little bit of an artifact in the those band ratio plots I showed, and that's due to actually using signatures derived from different grain sizes of the mineral. So there will be slight differences in the grain size, and it should actually, I think, hypothetically, I think it would actually affect the shape of the spectral feature slightly. But if it's a large enough feature, we should actually be able to resolve it regardless of surface roughness.
Great. Thank you.
I'm going to then follow up with a question that seems to be related to that, that's showing up in the chat from Nathan, who says the olivine on the moon example was really cool. How often can that process be used on Earth with all the vegetation and human land use?
So yeah, I mean, hypothetically, you would, thank you, well, first, thank you for the question, but hypothetically, you would, the process itself, the general methodology of using band ratios can be used in any environment for any target. You just kind of have to know how that, you have to have a little bit of knowledge of what you're looking for and how it responds, or there's reflected properties. One of the classic band ratios is called Normalized Difference Vegetation Index. So you can use that it uses near infrared and red bands to determine or to reference vegetation health. In terms of actually looking at rocks specifically, again, this work in the reflective work is generally going to be off the surface, so you're not going to get much surface penetration with that. So if your rocks are covered with vegetation, it might be difficult to do that, to measure them. However, if you want to actually get an idea of what your land surface is through vegetation, you can use something like Lidar. So that is something, there's a lot of civil use I've seen for Lidar out there. Most of it is flown, or a lot of it's actually on the ground. Some of my colleagues when I was at Idaho State actually used a terrestrial laser scanner to map the retreat of this thermal karst feature. So where the permafrost is melting and causing basically a big collapse of this land surface on a river. So they were able to map that with LiDAR. Does that answer your question, Nathan?
Oh, I'm sorry, I was muted there. Nathan has said in the chat that yes, it does. Thank you.
Great, thank you.
And then we also have a question in the chat from Dr. Jason Van Horn, who says, you used many sensors in the lecture. What is the ratio of sensors, private to public? Does the Air Force military rely on for imagery from private sources, Maxar, et cetera, compared to NASA and NOAA sensors?
So I'm not sure if I can get into just where we get our data sources from. I will say that we have the we do have the capability to utilize civil and commercial imagery. And there's actually several good articles out there on. There's several good articles out there on so how the NGA, so the National Geospatial Intelligence Agency, they're kind of the functional managers for imagery science and imagery analysis. How they there's some good articles on how they're utilizing commercial. Yeah, we definitely have the capability to use everything at our disposal. Whether or not we do actually use it is, whether or not it's useful to us is a different story. But we do have that the ability to access to that. I mean, civil sensors are free to access. So yeah. So thank you.
Dr. Sturley looked like he he might be having a comment about that.
Oh. That's because Adam was deliberately cautious about not revealing some of his job capacity there.
I will take this time to say that I am here as an individual, not representing the Air Force, the U.S. government, or any other organization. So nothing I say can be attributed to their beliefs. Just to cover all of us there.
And as you probably know from your time in the department, Dr. Sterling will try to push you to go to the boundaries of what you can or cannot say.
Yeah.
We currently do not have any additional questions in the chat. We are at the end of our formal seminar time, so I'll just take this opportunity to thank you very much, and again, assume loud clapping and cheers, and those who are able to put their reactions on the screen are showing their appreciation for the work that you have done. I'll keep this Zoom open for a little while longer. If there are some other questions that people want to ask, maybe you can just turn on your video and unmute yourself and ask the question of Adam. But thank you very much on behalf of the department for that very interesting talk that you've given us today. Thank you.
I really enjoy giving it. I enjoy talking about sort of what I do. And of course, seeing everyone here again, it's great to see you and see you all and hear what y'all are doing. So thank you.